Hi, everybody. This is episode 20, I think. It's amazing that we already did 20 episodes of the physics of Bitcoin. It's a show that we do every Wednesday. Well, it depends where you are. It's Thursday there, right? Where you are in Thailand.
Thursday in Europe and Asia, yes.
Europe, and Asia.
Yeah.
It's an international show. There are people everywhere. So, um, and the physics of Bitcoin, just so we always, it's a kind of a tradition now. We always give a little introduction about what it is. It's basically we are trying to cover different topics that are, let's say, more scientific, more technical, about anything related to Bitcoin. The Our angle is that both professionally, both I and Stephen are physicists, in particular astrophysics. This is where we come from. And then in our career, we did other things. I became a neuroscientist, and at a certain point, Stephen worked in more in computer-related topics. Our approach is that we bring our knowledge of physical system in trying to understand finance, and in particular Bitcoin itself. And you know, one framework we have, it's the power law, Bitcoin power law. That is our point of reference in many of these discussions. But it's not always only related to the power law. We have other angles that sometimes we use in trying to understand Bitcoin. But that is kind of a theme of this particular show, that we go deeper. Both in our work, we started to actually sometimes cover others people work, because there is I don't know if many people know that, but there are many papers, scientific papers written on Bitcoin that explore some of the mathematical, economical, even physics. I was looking at some of the publication. In fact, one of the publication I'm going to talk about today, they are published in physics journal, like Physic A. There is this journal, European journal called Physic A, where they are interested in understanding Bitcoin. Anyway, if you want to add to this description or some comments about the show.
Yeah, nothing much to add. We thank you for joining and sitting through. And if there are topics that are a little hard to understand, well, please ask us questions, and you can always, look at the show a second time, and maybe it'll become a bit clearer. Also, I put articles up on Substack that are related to the content, so that's another way to get a look at some of the details.
Yeah, and send me by chat your Substack, so actually I can make a link to it. So yeah,
I will put that in the private chat.
Private chat. Okay, and usually our tradition with Stephen goes first. We cover different topics, and he has a very nice agenda. I need to start to organize myself and having a nice looking agenda too.
Yeah, it's I think will be a little bit controversial too. So we will see how this goes.
And I will show you in a second. You will get the link in the video. You will see the link in a moment. So go ahead.
Okay. I'm going to share my screen. And okay, play. All right. So last week we talked about bubbles and how bubbles seem to be decaying over time, and that had been partially in response to a question someone had posed on Twixter. If there were no bubbles, would there be no power law? And my answer to that is really the opposite. The power law is more fundamental. Bubbles are things that happen on top of the power law. So we have power law plus plus, where the plus plus is the bubbles. But if they go away, we still have a power law. And so I'm going to get into some other analysis that supports that view of things. So here's the agenda. It's about smaller bubbles over time. And the first thing I'm going to talk about is a little bit in left field, but it's not entirely unrelated. It's about spacing in log time when you do regressions rather than in linear time, which is always what we're doing. And the second one is a reminder that bubble power is clearly falling. And then what I do after that is show studies that I've done in the past week about how the power law index behaves with time. And I've done this before in the past and have written about this. And basically, you see how the power law index oscillated and then settled down and has been pretty stable for a decade now. But the thing that I've gone beyond in kind of new research just this past week is to apply log periodic power series analysis, not to the prices of Bitcoin, but to the way this power law index develops over time. So I'm going to show you those and some interesting results. And I do it for both block monthly and regular calendar monthly analyses, and then for weekly analyses, because I wanted to see what the sensitivity is, how much different are the results, and they generally align with each other, but you'll see some differences. And the summary of all this is bubble dissipation. Bubbles really are dissipating. And I'll close with just a snapshot of the current market situation and where we would tick into bubble territory given where we are right now. Okay, so the first one, I've wondered about this for a long time, but I had never gotten around to running the model. You know, when we run our models, we have data series that are daily or weekly or monthly, and so they're all linearly spaced. But we're looking at something that's a scaling phenomena, a power law scaling phenomena. Really, you want to sample it more equally at log intervals, because that's where your regression lies. So what I've done is I've taken the weekly data, but I've only selected from it. I've sampled from it so that you'll have equal intervals in log space. And the way you do that is you calculate where all the equal intervals are. You then find the nearest 2 points on either side of that, and you interpolate. And then I've done regressions. So I've got 760 weekly values, but I've run regressions here that just have 20, 40, or 80 equally spaced in logarithmic age data pairs. And then, so what's the ordinary least squares regression slope for those? And so the top two are the 20 sample and the 40 sample, and then the bottom one is the 80 sample. They basically all give the answer, you know, that we're used to, which is about 5.8. The top one gives a regression of 5.92, and the next two 5.81, 5.82. They have excellent R squares. The R squares are 0.96 or 0.97. So I think this is something that validates, you know, everything that we do on the power law, but it also has some hints towards the idea that the bubbles are fading. And of course, you know, we see, particularly in the 80 sample, how those decrease. Okay, so if no bubbles, would there still be a power law? And what I've shown is that the power law can be applied to how the bubbles have fallen. And what I do is I measure the average bubble power for each of the 4 major bubbles that occurred in 2011, 2013, 2017, 2021. And that's the average. This measured is the average percentage over the lifetime of the bubble. And these things start, and they have basically an identifiable start, and they have an identifiable end when they get above, you know, the 50 or 60 quantile. You can choose however you want. I think I use the 50 quantile for these. And then you just take the duration, you take the integral under the curve, and you get the average power for each bubble. And you can see that both of these curves fit. The dashed red line is a reciprocal, inverse with time, but it has a little offset so that you don't have infinity at time 0. And it maybe doesn't fit quite as well as the power law. They're both equally good, essentially. And the power law is a minus 0.83. I show it separately below with a histogram, but it's the same sort of thing, where the bubble power, you know, is decreasing monotonically as age increases. I've labeled them with inverse of age in the histogram with the green bars there. Clearly, there's significant decline from 300% power down to, something around 70% in the last bubble. All right. Now, the next question is, how does the power law index itself develop with time? And I had previously looked at this in terms of block months, and so that's what's charted here, but I'm also going to show you for calendar months, slightly different results. The charts here are log linear. So we've got, well, they're not really log linear. For the price, they're log linear. So I've shown the price in orange, and the fit in the red curve is the latest version of the power law at the end with using all the data. But the blue curve says, okay, at any instant in time, looking backwards, what would I think the power law was? Only using the prior data to that time, right? So it's only looking back historically. And what you see is that it climbed up above 6, peaked in 2012, roughly around the beginning of 2012. It dropped back to 4. It climbed back up to 6, peaking around the start of 2015 or slightly before, dropped back down to 5, and then it settled in. So for the last almost 10 years, it's been settled in between 5 and 6, with a little bit of bumps due to the bubbles. Now, the power law index peaks after the bubbles because it's measuring during the bubble when it's not only when it's going up, but it's also being pulled up still when the bubble's dropping. So it's about a year after or so relative to the bubble peak. Now, the green line shows the uncertainty in the power law index, for that history at that time. So initially starts out quite uncertain. It's plus or minus about 1 or so. So you could say in 2012, it was like 6 plus or minus 1, right? There was a lot of uncertainty, but it steadily dropped off over time. And now it's only 0.1. Formerly, this is known as the standard error in the power law slope on a log-log plot. So that's all about the top chart. It's showing that the bubbles maybe helped the power law. It was sort of a driving force we talked about last week, potentially in helping the power law lock in. But it certainly locked in with or without the bubbles because they faded in importance. And then in the bottom chart, what I've done is I've done Sornet's log periodic power law series kinds of fits to the first 3 bubbles of power law index independently. So these are not log periodic power law fits to the price, they are to the power law index itself. And actually the fits are pretty good. They're not bad.
I love it. So just go back one more time. So you took the index and then you ran the log periodic power law algorithm on the index itself.
Correct. Correct.
Well,
and just for that particular bubble. So each one is a distinct fit around that particular bubble.
And then you found the one that had the highest confidence level. What did you do?
I've got some R squared on these later.
Okay.
I'll show you. The R squareds are, I mean, these are the best fits. And,
Did you found a critical time when you did that?
The critical time parameter, I don't know what it is here. It's basically using a 5 parameter. I'll show you in a second.
Okay.
So it doesn't have a critical time. It just has time from start of the bubble.
I see.
I'll show you what I used. I used the simplest form. It's a 5 parameter form.
Okay.
Here it is. So this version has the 5 parameters, and they're shown in bold: A, B, C, W, and phi. And this is kind of the simplest form of the log periodic power law, which can have 6, 7, even 8 parameters. And there's a trend component, which is the A and B terms, the first 2 terms. And then the complicated last term starts with C, is for the oscillations. And it has 3 parameters. And they're shown, what these are shown in the table there. But basically, A measures the core value, the basic value of the power law index at the start of the bubble. And the B term measures the trend up or down during the bubble. It's kind of a slope as how fast that power law index is increasing. And then you have an oscillating term, an oscillatory term. That's most clearly seen in the red with the first bubble, where you can see the oscillations, which are in the dash line, and the R solid line in red is the actual, sorry, the model is the dash line, the LPPS model, and the actual observations of how the power law index is changing is the solid line. And you can see that the model oscillates more than the observations actually did. But then for the second and third, it got damped down considerably. And so you don't see much in the way of oscillation. You see it a little bit. Any questions about this, Giovanni?
Why did you choose? Usually I thought that the first term is actually more like a power law. I mean, a line is a power law, but an extreme case of a power law, or a special case of a power law. But it doesn't usually T have some kind of power there. You don't allow for power.
T
So
can have a power. T can have a power. That's an additional parameter. I'm going to show that later.
Okay.
But I wanted to try the simplest possible model.
And what was your W? Do you have value for that? I'm interested in how fast it was oscillating.
Yeah, I'm going to show that.
The time scales.
I'm going to show that.
Okay.
And so remember, this is fitting to the power law index. So it just starts with a base value for A, right? Okay, now this is also monthly data, but it's not block monthly. This is calendar monthly. And actually, it's a little more extreme. The power law index observed goes up as high as 11 or 12 with calendar space data. And it has the same, kind of big spike up and then down below and then back up again around 2014, 2015, and then it settles in. So for a decade, it's been settled in.
Yeah. And by the way, I want to interrupt to make a comment. Anybody that claims that they could see a power law before it stabilizes, they are lying, because it was impossible to find a power law there. You can see it looks more exponential than really a power law. And if you want to fit a power law, it will have been a crazy power law with a very crazy high value of a slope. But you will never have thought it was a power law early on, because it was mostly dominated by that huge bubble. The huge bubble dominated the early data.
Right.
Do you agree with that?
Yes, I agree. So until 2013, really 2014, you wouldn't know.
Yeah, exactly.
Lo and behold, that's when that's the time frame when you discovered the power law nature.
Right. Go ahead.
Okay. So there's the price curve in green, the power law index curve in blue, and the uncertainty or the standard error is the shading around it. And you can see how it becomes much more precise. And then, looks like it's converging to an ultimate value. And then the bottom chart are the fits to the 4 major bubbles. And these are each individual fits. And you can see they're okay. They're not great, but they kind of roughly get it. It's very difficult to fit that first bubble. It's the model is too oscillatory, shall we say. And also for the 2014, but then by 2018 and 2022, we've settled down so much that it has an easier time fitting things.
Can I ask you, why did you decide to go with the exponent? I mean, I can see that they are related anyway, because we have the same functional shape. But why did you go with the exponent versus fitting directly the price curve?
Because no one has ever done this.
Okay. because you are saying that Sornet he has already Sornet, this physicist, he has already actually a paper. In fact, I can try to link it where he analyzed it. He didn't do the last bubbles, right? But he did analyze a couple of them. The paper is called "Are Bitcoin Bubbles Predictable?" Because supposedly this method can predict ahead when the bubble appear. And their conclusion was yes. So usually when there is a title, when there is a question mark in a title, the answer is yes, right?
Well, my title, the answer is no. If you remember what my title is for this talk.
Yes.
Yes.
Go ahead, sorry.
At
Yeah,
least
but I
probably
understand
not.
it's actually a
Look,
good approach to do it.
you know,
Yeah.
what he's trying to do is typically what people do in finance, which is they want to try to find a model that's predictive and they can trade on, and they look at daily data, and he's looking at the very fast oscillations and trying to identify the peak. He does a pretty good job of that,
Mm-hmm.
But
Yeah.
but his model is, I think, 7 parameters the way he runs it.
True.
Yeah. And so, what I'm trying to do was to get at something that's more underlying about the nature of Bitcoin and its behavior and the bubble's behavior. Yeah. And that's why I wanted to fit, I just out of raw curiosity to fit to this power law index and see if it would also map. And it sort of does into this framework.
And I like it because it really is really clear there is some kind of dampening effect, right? For a physicist, that looks like a dampening oscillator.
A damped oscillator. Yeah.
Yeah. It's like almost a textbook. It's really cool.
Now that begs the question of, can I fit the whole thing? So I'm going to get to that. But let me show you the weekly data.
I really like this. It's a really cool study.
It looks pretty similar. Just flashing between the two, they don't look that different, right? And so that's just validating, the resolution of the data and so forth. Again, the 4 fits, here the fits to the bubbles are a little bit better, I would say, at least by eye, because you don't have as many strange oscillations going on because you have better resolution. Okay, now here's what the parameters look like. Using the weekly data, same chart as I just showed on the prior slide. And the most important parameters for the audience listening in are the A and the C. So the A, remember, is the kind of more linear trending term. And essentially A is the power law index. And you can see it drops in the first bubble from 9.9. And this is validating what Giovanni just said a little while ago. You wouldn't be able to measure the power law in April of 2011. You'd get a highly discordant value. But by the end of 2013, it's down at 6.5. So it's starting to head to where it wants to go. And then 574 and 588, it's kind of arrived at, the overall power law behavior. And the B terms drop to nothing. And then the C terms are the oscillatory amplitude is the C value. And it's pretty large for the first bubble, but then it also drops to nothing. So it's just decaying away. And then there's your frequency term, Giovanni, the W, that's in radians, whatever that means here. I'm not quite sure. And then phi is a phase term. And then the last column you see R squared. And the R squareds are okay. They're not great for the fits. Okay, and then I look at a little more detail in that first bubble, the 2011 bubble, and the lower chart. And the actual measured slope is the dashed black line, and it's extending for about a year, a little less than a year. And then the fit is the blue line, and it has 2 components. It has a trend component, which starts around 10 and slopes up some. And it has an oscillatory component, which is added in to a green dash dot. and it's right on top, the because that is the two components give you the fit line. So okay, then I asked, well, gosh, can I fit all of these 4 bubbles with a single LPPL model? It doesn't work. It really looked terrible. So I backed off and said, okay, can I just fit 2 bubbles at a time? And that you can kind of do, but you have to add a parameter. So what you have to do is add in this decay in the oscillatory amplitude. So that's a power law of time, inverse. So instead of just a C term, it's a C / time to the power P.
Mm-hmm.
And the result was, the A looks like before, the C looks like before, but the p-value is minus 0.13. So that's a modestly declining power law there. I tried to run 3 bubbles. Even with decay, I couldn't do it. I couldn't get it wouldn't converge in the calculation. So I went on and did the second and third bubbles, similar thing, but now the P is steeper. It's minus 0.8. But
faster decay.
Correct. But it does not catch the turnover in the second bubble. You can see that it's heading upwards.
Do you know why? That was 19. Okay. Yeah.
That's the 2013 and 2017 bubbles.
Yeah.
Yeah. And then the third and fourth bubbles, the last 2 major bubbles.
Right.
The p-value is minus 0.5, and A is already down at 5.5, and it also fails to turn over.
Yeah, this one maybe I understand it because do you remember it was early peak? It was a peak in April.
Yeah,
there was kind of a little, in fact, actually, you could try to extend it and see if it catches the second peak. It was in 24. I mean, at the end of 2022. It doesn't even catch it.
Oh, these 2, it doesn't capture it. And actually,
it's supposed to be a second peak, right?
No, the April peak is, I argue, is bigger because it's a larger deviation from the power law trend.
Right.
Yeah.
But I'm saying you are showing only up to April. You don't go all the way to the end of it, 22, right? What if you
this
go
goes
to
into 2023? This goes to almost the beginning of 2023. It goes halfway through 2022 and more.
Okay.
Yeah, because the power law index peaks a year later. So the peak in the price was the last month of 2017, right? For the first one. But the power law did not peak until almost the end of 2018 in the index. Because what happens is you're throwing away lower power law index values by, right, pre-bubble data.
I see.
Yeah. So it peaks later.
Yeah.
Okay. So then I asked chat, well, what about the next bubble? Given what you know about these 4, what do you think? Well, we can already see that A stabilized, at 5 point something, above 5.5 in the 5.5 to 6 range. B is small and C is small. It's just noise. So a strong bubble like we saw for the first 2 is unlikely. If a 5th bubble occurs, it might peak late 2025 or in the first half of 2026. But the model implies it will be shallow, hard to distinguish from noise. So I have this quote from the treasurer of Sierra Madre, which I modified slightly. We have power law, so we don't need no stinking bubbles.
What was the original quote?
We don't need no stinking badges. You must have heard that one. It's repeated in additional movies.
I see.
Yeah. This is the original one. The Humphrey Bogart film, I think, was in it.
I'm going to check it out.
Yeah. Okay. Now I want to close with where are we right now? now that we're at 98,864, something like that,
Nice.
which we arranged, to have aligned with our show. The base Power Law Core has a slope right now of 5.9. That's the quantile 0.1. The middle one is 5.82. That's the median. And then if you can project, where are you at age 16.41 if you use the equations for those quantile lines? And the median is 87,000 for our current age, which is 16.41 years. So if you're at 99K, you're between the 0.5 and the 0.6. And it means we're at level 0.56. If you interpolate, you have to interpolate logarithmically to be precise. But
Right.
So we haven't reached the 0.6 level, so we're in the transition zone. And the 0.6 level is 108,000. So if we reach that, we'll be into bubble territory.
Mm-hmm.
And also, I want to put up the latest market cap numbers. Bitcoin is now, with this current price, past silver, and it passed Google, Alphabet. So there are only 4 stocks above us. There are only 5 $2 trillion and above assets if you round us up to 2 trillion.
Yeah.
And the annual growth rate with a 5.282 index is 41%.
Mm-hmm.
So you get that from the Power Law even without any bubbles.
Yeah, explain that formula to people, because that is a very handy formula that people can use anytime.
Okay. All you need 2 numbers. You need the age in years, which is 16.41.
Yeah.
So what you do is you take the inverse of the age, you add 1 to it, you raise that to the Power Law index, power. So if I take 1 over the age, it's about 0.06 right now, right? So then I end up with 1.06 raised to the 5.8 power. If you want, you could do a Taylor series on that, and you would say 0.06 times 5.8, right? Which is about 0.06 times 6. That would give you 36%. There's some additional terms in the series. So you want to do it precisely on your calculator, and you'll get a number like 1.41. And that's the ratio of the 1-year advance in price.
Yeah.
And then you subtract 1 and you get the percentage advance.
Yeah. Subtract and multiply by 100. Yeah.
Yeah.
Yeah. To get a percentage. Yes, it's fantastic. It's a very simple formula, right? So people can, if you want to know at any time, even in the future, right? So if you want to do the future, you take the age. So let's say 10 years from now, Bitcoin will be, in fact, can we calculate what will be in 10 years from now?
What the growth rate will be? Sure. Yeah. Let me just do that now. So let's say 10 years exactly, 2641. So we'll take 2641. We take the inverse of that. We add 1 to it. That's 0.037. So actually, if you multiply that number by 5.82, it almost tells you. But we raise that to the 5.82 power, and we get 1.24. So it'll be 24% 10 years from now.
Yeah. But so with 24% is still amazing in comparison with any other stock or any other asset. So even in 10 years from now, we will still be 24, because unfortunately this is, if we follow the power law, there are 2 good things, right? Let me say these in general. I like that we continue on the power law. I know some people don't like it because they think it's slow, etc. To me, it's a point of reference, because it means there is some kind of mechanism that is assuring this kind of scaling behavior. Nothing is assured in finance, but it seems a very solid. Stephen is showing how solid has been over the year. It's becoming better and better. So if we continue under this path, we can, have some level of confidence that we are going places, basically. And we can tell even when we are going, where we are going, and how long it's going to take. But you cannot say that with basically almost any asset in the world. So it's something that I think it's a very important property of Bitcoin, and it should be cherished if it is true. And it's
Yeah.
not that slow because right now we are doing 40%, 41%. In 10 years from now, it's still 24. It's still going to be amazing even after that. So, and by the time in 10 years, Bitcoin will be $1 million, So it's not that slow. And it's stable and resilient, So there are a lot of good things about the power law. Anyway, so this formula, write it down because it's a very simple formula. You can put it in your calculator. So put any age of Bitcoin. You can check in the past if you are curious. You will be mad because in fact, what will have been the first year? First year will have been two.
You don't want to know. It'd be 2 to the 6, which is almost 64, right? It would
Right,
be
64, right?
60
So the first
times.
stage, the first year, even if you take 5.8, it will have been
Yeah.
55 times, right? So you see, this is the idea of diminishing return. The first year, we went up 55 times, if you use the 5.82 number. But now it's going down, right? And it's 40%. But it's still amazing. And there are some good things about slowing down because it allows the system to stabilize. It allows the institution to come in. It will be impossible. Imagine if you had an asset that don't talk about 57 pair, talk about even 2 pair. It will self-destroy. It will not. The infrastructure will not be available. It will be impossible. So it's actually a good thing that is slowing down, not a bad thing. I know people are impatient, but actually, for the goodness of a system, for the stability of a system, power laws are perfect for this. This is why a lot of natural systems, like there is this entire article. Sometime, in fact, we can discuss it. That looks at the growth of many biological features, like the tooth, the thorns, the shells. They follow power laws for very precise reason because it's an optimal way of using resources if you have something that is growing over time. Nature knows, right? It's evolution. There is some selection process there. So Bitcoin somehow, because of all our interactions, has this wisdom that natural system develop over millions of years, and we did it in 15 years. It's pretty amazing. It's crazy.
The power law tells you that the probability that it gets to 1 million is higher, and the volatility will be less on the way there, because the power law also tells you directly that volatility goes down in percentage terms, not in absolute dollar terms, but in percentage terms.
Yeah.
And people tend to think in absolute dollar terms. They say, oh, it moves 10,000, 20,000. But that 20,000 is getting smaller and smaller in percentage terms every
Correct.
year. So power laws are stable. We've talked about cities as compared to companies. Companies last 10 years, 20 years if they're large on average. And, they have this exponential growth, but then they slow down drastically and they may even crash and have exponential decay. In physics, exponents are often associated with decay processes.
Yes.
And so what the power law is giving us is stability and lower volatility, and these make it with actually a more investable asset than it was 10 years ago when the volatility was so high. And that's why institutions are coming in now, because
Yeah.
the Sharpe ratio has improved, right? The return relative to the volatility, and also the size of the asset class, as we show in the other chart here at 2 trillion, is enough that it matters. You can get a big enough chunk that it matters to an institutional size investor.
Yeah. And in fact, I have another insight. It was very good that in the beginning, Bitcoin was growing fast because it allowed it to survive, right? It was like,
Right.
it's almost like a little lizard that needs to grow very, like, do you know how most animals, right, in nature, like a hoax, it comes out from the mom and it starts to run. It needs to run because otherwise it will be eaten. With a human being, you can take more time, right? Because we are a group, or we can protect our little children and so on. With a horse, you need to run, and this is what happened with Bitcoin. Bitcoin hit the ground and started to run. It started to grow so fast because it would have been killed relatively easy when it was small. But because it was growing fast, it attracted attention. People started to invest in it. They were curious about it, and so it was good for Bitcoin to grow that fast in the beginning. But over time, it needed to slow down. And that is also part of its survival, because otherwise it will have been collapsing on itself. It will have gone critical, it will have gone unstable, and will have collapsed it. So it's actually the perfect type of growth. It's very fast in the beginning, but then slowing down over time. So it's actually a feature. It's to have a power law. It's a very good thing for Bitcoin to be a power law.
So, yes, there still would be a power law, is my conclusion. And the bubbles are dissipating. And, expecting bubble behavior is not the Stoic philosophy. The pure T on the right is the Stoic philosophy.
Yeah, maybe it's boring, right? It's a little bit boring because we all go all excited, but it's also very heartbreaking, right? When you reach these large deviations and you think that you're super rich because your portfolio shows these crazy numbers, and then it crashes, right? Like it did in the past, 80%, So it's actually a good thing that these bubbles are dissipating and we have this steady behavior. It will be boring, but up to a point.
It's an adult perspective rather than a teenager's
Exactly.
perspective.
Yes. It's like, it's a cookie test, right? That actually the Bitcoin standard talks about, right? It's better to have two cookies later than one cookie now, Okay.
Okay.
All right. So I will share my slides. I want to talk about two topics. The first topic, I don't want to be controversial, but it's something that has been coming up a little bit recently. And then I will segue and talk about something along the same line. Basically, so this is about, there have been some claims that, and here the argument is now who was first, who was. It doesn't matter, like I make this claim that I was one of the first people to notice the Bitcoin power law. This is for example, a Reddit post I posted in 2014 where I mentioned the Metcalfe law in Bitcoin because I noticed a power law. In fact, I say this story many times. It started by me watching a video from Jeffrey West, that is an expert in power laws in social system like cities and corporation, etc. He studied this. He has an entire beautiful book. I saw a video on him by him discussing these things, and I had this intuition that Bitcoin was following the same type of behavior. I was familiar with the power laws because physicists encounter them all the time. I didn't know the relevance for social systems like cities because so you specialize in a field. I never heard of this idea of power laws in social system like city. So I went immediately to check Bitcoin, and I found all these beautiful power laws. This was in 2014. The one that I found later, there was because I was still struggling to understand how Bitcoin was growing in time. I was doing indirect things using this other property, the relationship between price and addresses and price and transactions. And then I realized that actually Bitcoin is a power law in time. That means actually it's the product of two power laws. It's how the addresses are growing, that is also power law, and then how the price reacts to the addresses, that is a power law. There are two power laws that combine to each other, and then they created this power law in time that we observe. It is really interesting, very fascinating. But there were other people who were on the same track, and we were trying to explore things, and we were trying to understand Bitcoin. I quote all the time Trollolo, but sometime maybe we can talk about that model, because it didn't specifically mention power law, but he had some intuition in that direction. And then there is this other OG. He was operating around this time in 2011, and some people are claiming, oh, that was an attempt to actually describe the power law in time. It's not, and it will be, if there is somebody that did that, amazing, right? I will not have any problem, but it's misleading, because then, the goal is for us to understand what is going on. If somebody's trying to tell us, because it would have been amazing, somebody noticed a power law in time, at that time, when the data didn't allow, like we discussed it. How could it be even possible? So, I care about people understanding things. And so if you're saying wrong things about Bitcoin, or somebody modeling Bitcoin, the record needs to be, it needs to be made straight. So read my article if you're interested, because mostly what happens is, this person gets some credit, but what he says from the article itself, it's a study on ownership. Bitcoin ownership obeys a power law. That is a good intuition, but this model that is proposed, and the model is described here, is not a real model, because you can see it's a very artificial one, right? What is proposed, notice what happened. And in fact, I would like to know, on a certain point, I'm talking with this OG. He's active on X, so we started to talk, and I'm trying to understand from him how he came up with this model. But you can see it's a very artificial model. It's not based on data. So if you, the only way to know that we have, right, that is reasonable to know ownership, is to look at addresses, how addresses are distributed. It's a proxy, because it doesn't tell us the exact number of users. And maybe sometime we can study how can you go from addresses to people. And there are probably you will have to come up with some kind of conversion. I say, okay, maybe the average person has this number of wallets, etc. So then you can convert addresses, because one person can have more than one wallet, right? You can go from wallets to people. But to me, it's actually addresses. When I start to think, it's a very good measure, because it doesn't matter if you have a lot of addresses, you're acting like many people, because you are creating a lot of activity on the network. So it's actually a good measure of network activity. But this person was trying to make sense of adoption. So, he gets all the credit in the world for this, but he made kind of a theoretical model, because you can see it's very artificial. It goes up by 10 every single time, 10, 10, 10, 10. And then he reduces. I don't know what he means. I don't know, because it's not super clear, but probably means like an average ownership of Bitcoin. But it's weird, because after 1 year, we will be 10 users. So I don't know. I would like to understand better what was meant here. But you can see it's very artificial, 1, 10, 100,000. So I look at the data of addresses. It doesn't look anything like that. Because right now, for example,
Giovanni,
yeah,
he's basically assuming a Zipf's law. That's a
it's a Zipf law. It's one over. It's like an inverse law, right?
It's a -1 power law, and the
Exactly.
important thing for people to understand is what's the dependent variable and what's the independent variable.
Right.
So here, the dependent variable is the number of wallets. Sorry, it's the number of wallets for a given balance, and the independent variable is the size of the balance, right? How many?
Exactly. Yeah.
When we talk about price and power law, our independent variable is something entirely different. It's time. It's age.
And so this is called a distribution properly, because it's basically a statistical outcome. You're saying, you're looking at the statistics of something, and then you create like beans, what we call beans. And you say, I want to look at how many people there are that own this number of Bitcoin, and you come up with a bean, right, that represents that group of people. When it's basically you will create what is called an histogram. A distribution is associated with an histogram. It's not a function. And so this is a distribution. He's right to call it a distribution. And it's very different from what we talk about. It's still an early attempt to understand Bitcoin mathematically. Great. It gets a lot of, but it's not absolutely what we discuss, because people stop here and say, oh, look, he's talking about power laws. Great. He's talking about log graph. Yes, it's, if you look at Wikipedia will tell you that a power law looks like a straight line in a log graph. And in fact, I try to reproduce his data, and it looks like this. Okay, users here on the y-axis and fraction of total health. You can calculate it in terms of Bitcoin. This is how he explained it. I did it in fraction of the total wealth. I calculated how many Bitcoins there were. I summed them together. And then this is called a distribution, because it tells us, given a certain amount of wealth, how many users there are with that wealth. And it looks like this. It's basically close to 1 over, basically inversely proportional. In fact, actually, the slope turns out to be minus 0.8. And the R square is very good. It's 0.98. So you can see this is the straight line that he's talking about, because it's the only straight line that there is. Because actually, the other information that he's giving in this imaginary model, also this needs to be understood. This is something that he's guessing. He's also say that this is basically a guess, right? He say this is a rough guess. And also the timeline, it's a guess, because we don't know, unless you're using addresses and then you go from addresses to users, he's making a guess, right? And if you look at the guess, because I also did that, I really went to study this deeply and trying to understand. It's actually an exponential, because here I see his user and his time progression from time 0 all the way to the projection. He has a couple of projections for the future. It looks like an exponential with a very, very good fit. So it's not a power law, it's an exponential. And then he says, okay, we can maybe extract the price from this model, because I can project it in the future. I don't know how exactly, because he doesn't provide formula. It seems probably he did it manually, where he kind of draw the line and he projected in the future by extending it, because he doesn't have a formula or anything like that. And if you do that, because from the projection, you can deduce, because it gives us 3 value for price. Okay, the current price, it was $20. When it goes to $100, when it goes to $1,000, you can see again it's a very artificial sequence of prices that it says his model predicts, and they are perfectly proportional to the number of users, 1 to 1. And we know that it's not true. It's a non-linear relationship between price and user, because the real data tell us there is a non-linear relationship square. This one is a kind of a theoretical model. If you want to still man this approach, you're making this assumption that we are linearly related, and it fits with these numbers. These are the numbers it gives. It's perfect linear relationship, R square 1. And then you get a model out of that, and this is the model. So whoever says that model, because, for example, Sina, I'm sorry if I go now a little bit, and I will try not to make it personal at all, made this claim that is not true, that basically he took my model. He say, I still don't understand, because he claims that if you just take data up to 2012, and it will be almost a perfect fit to today. I don't know how you could do that, because we already demonstrated that you will get, or even if you went ahead and you say you had a model of a power law in mind that is not true, you will still get a horrible power law by just fitting the early data. You don't get our current power law, but it was not a power law. It was an exponential model if you study, and you can read it and you can, and he actually himself, he says, I never said that I invented the Bitcoin power law. He even says that. So this is Jim. So he clarifies that this is not what he had in mind at all. Okay. So I want to I want to um, kind of clarify this issue because it's something that can confuse people, right? It's not about who has the priorities. Just if you claim that there was a model, it's also interesting because at a certain point, Bitcoin will become uh, something that will be taught to children. It will be in textbooks, and there will be big history of Bitcoin modeling, Bitcoin discovery, and so it's important to keep the public well informed. You should not tell things that are not true. And I try to describe here. It's interesting because if you want also to learn about how to model something, etc., maybe you can learn something from this article. Okay, this is all what. Do you have any questions, Stephen, or maybe comment on this if you want?
No, I think that was clear. There were two things. One is he was not modeling price versus age. He was
Yeah.
modeling the distribution of wallets, and which is a static thing, not a dynamic thing. We're talking about a
Yes.
dynamic development of price with time, and the
Yeah.
wallets with the balances and the number of users is a snapshot, a static thing.
Yeah.
And the second thing, of course, is that you really couldn't at that time find in the data the power law because things were so noisy. It was too
Yeah,
early.
and there was a huge big bubble in 2010
Yeah.
that dominated everything, and it was impossible basically to find a power law there. In fact, many people were simply saying, "Oh, we are exponential," because we were looking, and then actually we went in the opposite and say, "Oh, this is tulips." Remember at that time, "Oh, this is tulips. This tulip." You see, we went up. We reached. What did we reach? Like we was like $20 at the peak of the bubble. And then we crashed to $3 or something like that. And people were saying,
Something.
"Oh, it's tulips." This is Bitcoin is dead. This is what people were saying. And so, it's important to clarify these things. But anyway, so let me go ahead. Maybe we have a few more minutes. And I use this actually as an opportunity to study and understand um, wealth distribution. Actually, the real, not an imaginary model that, again, you get credit for it because it was trying to make sense of Bitcoin, that is always fantastic. So Jim gets all the credit in this world for trying that. But if you actually look at the data, um, you can learn something from the real data, from the it's called a rich list, right? It tells you who owns what in terms of the addresses. Addresses, it's a proxy, but it's the only thing we can use, to make sense. Now you can try to make a model, but it will be a theoretical model of how many addresses a certain person has, and one could try that. But in general, um, it's simply better to look at the addresses. We call it, and you can tell me if you agree with it, with this. We call it observables. We in physics we rather look at the things that you observe directly and describe that, and then maybe from that derive some other quantity that you don't observe directly. But we always start with what we observe. Do you agree with that? Is the physics way of doing things?
Of course.
Yeah. So addresses, it's our observable. We don't observe users. We don't know how many users there are. We have addresses, but I don't know how we do this rich list for other assets. Maybe taxes, maybe some other approaches. But there are rich lists for, for example, just wealth, normal wealth, not the wealth in Bitcoin. And so I was studying this paper that came out a few years ago. This is actually in a physics journal. And they were looking at distributions because physics studies this thing, studies also financial and social data using the language of physics. And power laws is one of the tools that we use all the time. So we're trying to make a point, are these the real power laws? So we're trying to really to go to the details where, okay, you can see it deviates at a certain point, right? And there are reasons why there is this deviation. But a power law is a relatively good fit. Do you have an idea why do we have these deviations, Stephen, from power laws on a certain point?
This Are you asking for Bitcoin in particular, right? Yes,
No, but
or
for
in
this,
general,
yeah, in general.
for wealth in general.
Yeah,
Yeah, well, most people have heard of the 80-20 rule, right?
yeah, exactly.
Yeah, which is kind of Pareto encapsulated. Pareto's law is a power law. Zipf's law is a particular form of that, which is, a reciprocal, a -1 index. Look, the rich get richer,
Yeah, it's
and
mostly because,
the rich
yeah,
have
because
many ways to get richer. They just have
the
many more
reason,
devices.
one of the reasons why you get these, in fact, actually, one day I want to cover this beautiful lecture from this econophysicist that he made models of why this happens. And one of the reasons why this happens is that when you have money, you can reinvest the money, and
Right.
basically you're going to get multiplicative effects, because power laws are results of multiplication. You amplify by multiplying, so you don't get 1 plus 1, 2 plus 2. You get 2. Okay, 2 plus 2 is still 4, but let's say 3 plus 3, you get 6, right? But 3 times 3 is 9. You get, if you have multiplicative effects, you get bigger number. 10 plus 10 is 20. 10 times 10 is 100, right? When you multiply things, you get bigger effects. And so, and this is what happens with the rich people. They can reinvest their wealth because they don't have to use it all to survive. And then that makes them richer. And this is why over time you have these distributions that have very, very long tails. Yeah, basically means a lot of wealth is in the hand of few people. And one of the way to measure how fair a distribution, right? And fair can mean many things for many different people. Of course, right? It Some people get rich because of inheritance, but other people work hard for it. But so let's not go into politics, just the math. But if you wanted to know how fair is the distribution, in the sense how well distributed it is among the participant, one way is to measure the slope. So and what is your intuition, guys? It's a steep slope more fair, right? If you have a very steep slope, or something that is more shallow, right? Which one is which? Well, it turns out that steeper it is, better it is, because it means that more people are within a certain range of wealth, right? As you go on the x-axis, so you're adding more and more wealth, uh, you're getting more and more people, right? That means they are close. If this was spread around, it means that you need to go to a lot of wealth before you capture the entire population, right? And so that means a lot of wealth is in the hand of few people. And we have data here. In fact, over time, it's pretty stable for the world, also for United States. In fact, if anything, it becomes a little bit less, because remember, steeper is better, right? In fact, you can see that over time in the US, at least, uh, is becoming less fair. There is more concentration of wealth over time. It's an empirical information. In China, it's actually a little bit more fair, because, in fact, if anything, maybe because of their economical boom or whatever in the last few years, is a little bit higher than the United States. And in fact, it went up instead of went down. Now, Russia is very unfair, because you can see it's 1.8, that means oligarchs. This is why we say that in Russia, there are a lot of oligarchs, right? Where the wealth is very concentrated. Now, what about Bitcoin? Well, so remember, is that Jim's theoretical model said 0.8. That was very unfair. This one, it's a little bit more fair, but less fair than the the economy of the world or United States. First of all, it's not really a power law. You can see that, but this is mostly dust, right? So these are small quantities. So if you start to see this 10 to the 0, I'm using the scientific notation, means 1 Bitcoin. So if you're looking at 1 Bitcoin and above, then it becomes more like a power law. Start to look more like a power law, like the tail of this distribution, and the slope is this. That means, yeah, go ahead.
Yeah, there's a problem here, which is, you're talking about distribution of wealth, and we think about individuals and rich individuals. But here, the largest wallets are held by exchanges
Right.
and by organizations. And so they're holding balances on behalf of many, many people.
Yes.
So it's actually, if you broke it down, would be steeper.
Right. So it's something that I don't know how to do. It would be interesting how to do that, to actually include that. And so, but it's a very important consideration, right? That actually these exchanges or the ETFs, etc., they represent a lot of people. And so that could be what makes this very steep. So I'm just mentioning this because once in a while you see this article that say, oh, Bitcoin is like North Korea, it has the wealth distribution of North Korea. You have to be careful. First of all, what do they mean? So now probably you understand better what we mean, but also maybe we find a way. I will look into it, how to come up with a conversion of that that consider that these large wallets should be broken down, because they actually represent a lot of people. But the data is the data, and then you can integrate, right? You basically can sum, you can do a cumulative sum. Basically, this is telling you, when we reach one, basically everybody's included, and it's telling you how much, basically the percentage of a ratio, right, of the total amount as a function of Bitcoin held. So, for example, if you look at more than one Bitcoin, you get almost 90. You basically, if you go all the way to one Bitcoin, you have only 2% left. So 2% is anything larger than one Bitcoin is in 2% of the wallets, it looks like. So, but this is how the data looks like. What is the interpretation? We can discuss it, but yeah, we need to correct for large institutions. So this is what I was playing with in the last few days. Okay, we can look at some questions. We have a comment that is a nice comment. People are celebrating the 100K. That it seems that we are going in the direction. Close. Keep this presentation discussion. We are watching money attention. Yeah, it's fantastic, right? To understand Bitcoin. Otherwise, okay, maybe we do have. We have this question.
Well, the data source is just the historical Bitcoin prices. I use the weekly and monthly prices. You can get those from places like Glassnode, but you can also get those for free at investing.com. You can get Bitcoin prices, download them. So any data source that has, it's just the Bitcoin price history that ultimately goes into the LPPL model. And from that, you compute the power law index as a function of time. And from that, you apply the LPPL model to the power law index as a function of time. So it's, a couple of stages in there.
Yeah. Okay, guys. I think we covered a lot of interesting material. We will be back next week, and let's celebrate this run up. It's really exciting. Maybe tomorrow we are 100K. Okay. Bye, everybody.
Thank you, everybody.
Thank you.
Thank you.
Thank you so much.